This is a help video for the alcohols section of the notes, starting on page 10. I'm going to put some timestamps in the description so that if you're stuck on a particular page that you can jump to the part of the video where I talk about that particular question. I'm not going to go through how to do every single question. I will go through some, and then for others I might just give you a hint about how to get started. I'm going to begin by just talking about alcohols in general. So when you think of alcohol, you probably think of alcoholic drinks. That's probably the most likely thing that would come to mind. And when you're thinking about the alcohol in alcoholic drinks, chemically, that alcohol is known as ethanol. We can also call it common alcohol. It's the most common one that we find. Now I've got the Molly mod for ethanol here. Okay. And the Molly mod gives us the molecular structure of ethanol, and we can start to link the molecular structure to the name to remind ourselves about a few aspects of alcohols. So the name tells us a little bit about the molecule. The eth part tells us what? Hopefully you're thinking 2 carbons. So ethanol is a molecule with 2 carbons. And then the ol, what does that tell us? Well, it tells us that it's an alcohol. And a little bit more specifically, it tells us that it's an alcohol, and alcohols have what we call a particular functional group. And the functional group is the part of the molecule which gives it its reactivity, it gives it the property of a particular family. So the group that gives the alcohols their property can be seen in this structure. What do you think it is? I wonder if you can either point at it on the structure or perhaps even remember the name. Okay, well, the part of the structure that gives the alcohols their functionality, that makes the alcohols, is this oxygen and hydrogen atom here. So remember, red represents oxygen, so we've got 2 carbons joined together in ethanol, and then we've got an oxygen joined to a hydrogen coming off one of the carbon atoms, which then also just has these 2 hydrogens. That is known as the hydroxyl functional group. And it is an OH group on a molecule. So the ol ending tells us that the chemical is an alcohol and that it has the hydroxyl functional group. Okay, so let's get started on page 10. Page 10 starts by giving you some properties of ethanol. So ethanol is a soluble, colourless, covalent, pH neutral liquid. So it's soluble, and really what I mean by soluble is soluble in water. And you can tell that ethanol is soluble because in your glass of wine you don't have 2 separate layers. The alcohol is mixed in nice and evenly with the water. It's also highly flammable, so you might have this tradition in your family at Christmas, but you can pour some strong liquor such as a brandy over a Christmas pudding and then set it on fire, and alcohol burns with a nice clean flame. That means that your Christmas pudding doesn't end up all sooty. Okay, so it's soluble in water since it can form hydrogen bonds. So remembering back to our first topic on intermolecular forces, we've got this phrase, like dissolves like. That means that substances with similar intermolecular forces are more likely to be soluble in each other. So water is highly polar and can form hydrogen bonds. Ethanol, because it can also form hydrogen bonds, is therefore then likely to be soluble in water. And question 1 says, draw a diagram to show the hydrogen bonding between water and ethanol. So if you want to, you can pause the video right now and see if you can have a go at that question. If you haven't paused the video, then I'm going to start by giving you some hints and see if you can get it from there. So, the first thing that we would need to do is we would need to draw the structure of ethanol. Now in your notes here, you've got the full structural formula of ethanol given down here. We'll talk about that again in a little minute. So we're going to draw out this full structural formula of ethanol. Okay, and then we're going to also need to think about the structure of water, and I'm just going to draw my water molecule over here for now. And then after that, I'm going to draw it hydrogen bonding to the ethanol. Okay, so what we need to remember is that hydrogen bonding is an electrostatic attraction. Electrostatic attractions are always between positive and negative. And when it comes to intermolecular forces, we're looking for the what we call delta positive or slightly positive and slightly negative parts of a molecule. So what I'd like you to do, if you're struggling a little bit with this question, is to look at these molecules, and I would like you to go to the data book and find the electronegativity values for carbon, hydrogen, oxygen, and and I'd like you to annotate your diagram with the electronegativity values, and I'd like you to use these to decide which parts of these molecules are slightly negative and slightly positive. So pause the video now and start. Okay, so what we find is that oxygen is the most electronegative atom in these two structures, and that means oxygen is going to pull the electrons towards itself. So your oxygen atoms in these structures are going to end up slightly negative. Your hydrocarbon part of your ethanol, we're going to consider that to be non-polar, so we're not going to consider any delta pluses or delta minuses over here. And then hydrogens are an electronegativity of 2.2, so when the oxygen steals these electrons, it's stealing them from these hydrogen atoms, and our hydrogen atoms are going to become slightly positive. So when we draw a water molecule forming a hydrogen bond with an ethanol molecule, remember hydrogen bonding is just a special extra strong electrostatic attraction that's formed when we've got an OH, NH or FH group, but the attraction is going to be between the delta positive hydrogen on one molecule and the delta negative oxygen, nitrogen or fluorine on the other molecule. So we can draw it in two different ways. We could either draw a line, and we draw a dotted line, remember, to represent intermolecular forces. We could either do that dotted line between the H on the ethanol molecule and the O on the water, or we could do the dotted line between the O on the ethanol molecule and the H on the water. So I'm going to draw my water molecule with a dotted line from this oxygen to the hydrogen of the water molecule right here. If you were given this type of question in the exam, you wouldn't need to put in the delta positive and delta negative, but you would need to get it the right way around. So the intermolecular forces should be drawn with a dotted line between the electronegative atom and a slightly positive atom. This next little bit of the notes just reminds you about the hydroxyl functional group. So you should be able to recognise the hydroxyl group in a molecule, and you should also be able to circle it in a structural formula. So if you were asked to circle the hydroxyl group in the structural formula of a molecule, you want your circle to go round the O and the H. The carbon does not form part of the hydroxyl functional group. When we draw the shortened structural formula for alcohols, it's very similar to the way we've done it in the past. A little point about the molecular formula. You'll see here that we've written the molecular formula in the way that you would perhaps expect by just counting the number of each type of atom, so we get C2H6O. But C2H6O could actually refer to several different types of structure. So quite often when we write the molecular formula for alcohols, we write the number of carbons and hydrogens minus the OH group and then the OH group at the end. So instead of C2H6O for ethanol, we would write C2H5OH. And this just highlights the hydroxyl group to make sure it's clear that this is an alcohol. So I would tend to use this one here, but it doesn't really matter. Okay, so the next section of the notes, this first part is talking about common alcohol. In general, alcohols are quite a broad class of compounds in chemistry, and any substance which contains this OH, the hydroxyl functional group, could technically be classed as an alcohol. But if we're wanting to stick with slightly simpler structures, then we can look at something called the alkanol family. So the alkanols are a homologous series of alcohols with the general formula CnH2n+1OH. So really the alkanols, we've got this "an" part of the name. "An" means that there are only single carbon-to-carbon bonds. And that's what makes the alkanols relatively simple. Okay, so we could get other varieties of alcohol, but the alkanols only have single carbon-to-carbon bonds, and also there would only be one hydroxyl group within the alkanol family as well. Okay, so anything that follows those rules would be considered an alkanol, and the alkanols have this general formula, CnH2n+1OH, and they are derived from the alkanes by substituting a hydrogen atom with an OH group. So what I mean by that is if we take an alkane like ethane, we're just going to substitute a hydrogen atom, take away that hydrogen atom, and add on an OH group. So that's what we mean by substituted for by substituting a hydrogen atom with an OH group. And as you can see, the name of the alkanol is obtained from the name of the alkane, but by replacing the E ending the final letter of the alkane with ol. So this table should be quite nice and easy for you to complete. I'm not going to go through this, but you can use BBC Bitesize or any other resource if you would like to. So you should have completed the table on page 10 yourselves. I'm now going to move on to talk about page 11. Page 11 I should really have given the title Properties of the Alkanols. So you might want to add that in. Okay, and we're going to talk about the type of physical property that we generally talk about, things like boiling point and solubility. So question 3 says, why does ethanol have a higher boiling point than propane and alkane with similar number of electrons in its molecules? So in this type of question, you always are going to want to talk about the type of intermolecular forces and the relative strength of the intermolecular forces. If you want, you can pause the video now and try and answer that question. What I would say is something along the lines of, well, if it's got a higher boiling point, it means it's more difficult to separate two molecules of ethanol from each other. So I would say ethanol has stronger intermolecular forces. And then I might give a little bit of an explanation. So it says propane has a similar number of electrons. That means it's going to have a similar strength of London dispersion forces. So both substances and we can use the abbreviation for London dispersion forces, LDS there. But ethanol has also got an additional intermolecular force. Thinking back to the previous page, what extra intermolecular force does ethanol have? Well, it's also got hydrogen bonding. Okay, so you don't necessarily need to give as much detail as that. It would depend on how many marks the question is worth. Question 4 then, state why the boiling points of the alkanols increases as the molecular size increases. Again, I'm going to give you a minute and see if you can answer that question. So again, just like in the previous question, what you want to be thinking about is you want to be thinking in terms of the type and strength of the intermolecular forces. So we're going to start with type. What type of intermolecular forces do the alkanols have? Hopefully you're thinking hydrogen bonding and London dispersion forces. So all alkanols have hydrogen bonding. I'm going to say conform hydrogen bonds again. Okay, so all alkanols can form hydrogen bonds and have LDFs, but as the molecular size increases, that's going to affect the strength of the London dispersion forces, because the more electrons in the molecule, the stronger the London dispersion forces. Okay, and then we're going to move on to the lower solubility of bigger alcohols. So on the previous page we already said that ethanol has high solubility in water. Ethanol is soluble in water, but when we get longer alcohol chains, the alcohols tend to decrease in solubility, so it might be worth adding that note in here. So as the alkanol molecules increase in size, their solubility, and again I'm talking about solubility in water, I should really specify there. As the alkanol molecules increase in size, their solubility in water decreases. So the explanation of why the solubility decreases as the size of the molecule increases is given in this little section here. So let's imagine if we've got, say, 5 carbon atoms in each alcohol molecule. So that's represented by these structures here, the black carbon atoms just with the OH group at the end there. So when we've got 5 carbon atoms in the alcohol molecule, we still have this OH group at the end which can form hydrogen bonds with water molecules. But the hydrocarbon tail doesn't form hydrogen bonds, and that part of the molecule is insoluble in water, and this decreases the overall solubility of the alcohols. So it's worth annotating this diagram a little bit, because remember, water is a highly polar solvent. And what we can do is we can actually talk about this molecule in terms of slightly different polarities and different parts of the molecule. So these alcohol molecules have a polar OH group, polar hydroxyl group, but then they also have a non-polar hydrocarbon, we could call it a hydrocarbon tail, or a hydrocarbon part of the molecule, or even a section, which I think is what I'll call it here. So we've got a polar OH group and a non-polar hydrocarbon section. And the larger the non-polar hydrocarbon section, the less likely the molecule is going to be able to dissolve well in water, because water is a highly polar solvent, like dissolves like, and if we've got a bigger portion of the molecule that is non-polar, it's going to be less soluble than if the alcohol is mostly a small molecule with a polar OH group. So in question 5, you have to explain why ethanol is more soluble in water than pentan-1-ol, and I would recommend that you talk about polar and non-polar, the polar section and the non-polar hydrocarbon section, and that you talk about the polarity of water as well. You can pause the video now and see if you can answer that question yourself. Okay, so what I've written is ethanol and pentan-1-ol both have polar hydroxyl groups, or OH groups, which dissolve well in water, a highly polar solvent, as like dissolves like. However, pentan-1-ol has a larger non-polar hydrocarbon section of the molecule, which decreases its overall solubility. So something along those lines in there would be great. It's actually quite interesting, this issue of solubility, and if you're interested in sort of the energy aspects and finding out about that in a little bit more detail, I would really recommend that you have a little look at that Chem Guide link just there on the page. Okay. So we're going to move on to page 12 now. Page 12 and 13, and I think actually 14 as well, are all focused on the naming of different isomers of alcohols. So when we have alcohols, we can sometimes have different structures but with the same molecular formula, and they can still be alcohols as long as they've got the OH hydroxyl group. Now, I think that given your previous knowledge of naming alkanes and alkenes, and given this example on this page here, that you should be able to manage with the naming of the different isomers of alcohols reasonably well. What I'm going to do is I'm going to allow you to finish page 12 yourselves, I'm going to skip on to page 13. So what you might want to do just now is pause the video and complete page 12 before coming back to the video for page 13. Okay, so if you're coming back to the video now, you should have already completed page 12 and we're going to look at page 13 briefly together. So page 13 starts talking about branched chain isomers of alcohols. And when we are naming a branched alcohol, we must include the position number of the hydroxyl group as well as the name and position of the branch. Now, the name is based, this is very similar to naming alkenes, so the name is based on the longest carbon chain which includes the OH group. So just how alkenes have to include the double bond in the longest chain when we're naming, with alcohols we have to include the OH group in the longest carbon chain. And we number the chain from the carbon closest to the OH group. And we're going to again, just like with other naming, we're going to write the name and the position of the branch at the beginning of the name and then the name of the main chain at the end of the name. So this one, just to run through where this name comes from, we have got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5 carbons if we go along this way, also 5 carbons if we go around the corner. So the easiest thing would just be to number the carbons, call this the main chain here, and number the carbons starting from the end nearest the hydroxyl group, 1, 2, 3, 4, and then we've got a methyl group coming off this chain. So this is going to be 4-methyl pentan 1-ol because the hydroxyl group is on position number 1. The reason I'm wanting to talk through this with you, I think hopefully you'll find that reasonably easy to understand, the naming of this, but I want to just run through how to draw the short and structural formula for this molecule. Because you'll have to do the short and structural formula for some branched chain alcohols over on page 14. So we're going to again just take each carbon in turn to draw the short and structural formula. So this first one, you've almost got a semi-short and structural formula here, but I would prefer you to use brackets. So the first carbon at the end is a CH3, then we've got a CH with a methyl branch. So again, just like we did with the alkanes and alkenes, when we've got a branch, we're going to put it in brackets. Okay, then we've got CH2, CH2, 2, 3, 4, and then we've got our CH2OH here. Okay, so question 8 then tells you to draw the following alcohols. Again, I think you should manage this. You're gonna just work backwards from the name. So 2-methyl propan 1-ol. You would start by thinking, well, how many carbons are in the main chain? So remember, the main chain is the second part of the name. Prop means there are 3 carbons, so we're going to have 3 carbons in a row. To 2-methyl, so we've got a branch. Meth means 1 carbon. We've got a branch with 1 carbon on carbon number 2, so either way we go, 1, 2, 3 or 1, 2, 3. The middle one's going to be carbon number 2. And it's propan 1-ol, so our OH group is going to be on the first carbon here. Okay, so I'm sure you're going to manage to do the next few of those yourselves. Okay, so by now you should have finished page 13, and I'd also like you to have finished page 14 before watching the rest of this video. So I'm on page 14 just now. Page 14 is just completing the branched chain alkanols table on this page. If you haven't finished page 14, pause the video now. What I'm going to do is I'm just going to go through the middle example on page 14 just so that you can check that you're going along the right lines. Okay, so first we're going to name this. So the name, remember, we're going to find the longest chain and then number the carbon atoms starting with the end closest to the OH group. So our OH group is here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7. So the longest chain is the one going across here. The OH is on number 2, 1, 2, 3, 1, 2, 3, 4, 5, 6, and then the methyl group is on number 6. So this is going to be 6-methyl there are 8 carbons in the chain, so this one is based on octanol, octan, 2-ol. And then I'm just going to run through the shortened structural formula for this one as well. So just like in the examples in the first section on naming alcohols where it gave you some examples of shortened structural formula, I've put the hydroxyl group in brackets. Sometimes it's worth just double checking you've got the right number of carbons in a shortened structural formula. So I remember anything in brackets is a branch, so I don't have to count that as my main chain, but I've got 1, 2, 3, 4, 5, 6, 7, 8 carbons in my main chain, so I know I'm okay with that. I'm just not going through these other ones because I want you to make sure you do at least some of the examples yourselves, but I'll mark them when you submit your work on Teams. In this final part of the video, we're going to continue looking at alcohols, but now we're going to look at some different ways of classifying alcohols. Up till now, most of what we've done has been a revision of National 5 and of the Unit 1 material on intermolecular forces. This is new stuff on alcohols relating specifically to higher chemistry. So if you look back to your learning outcomes, then the learning outcomes that we're going to go through in this part of the video is I can classify alcohols as primary, secondary or tertiary, so that's the first thing that we're going to look at, this way of classifying alcohols, and then we're going to learn what is meant by a diol and a triol, and you should be able to give an example of each, and for that example, for diols and triols, you should be able to draw the full structural formula from memory. Okay, so we're going to page 15 of the notes here, and we're going to start looking at primary, secondary and tertiary alcohols. So what it says here is alcohols can be classified as primary or classed as primary, secondary or tertiary depending on the position of the hydroxyl group. And it might be worth thinking at the beginning about what is meant by primary, secondary or tertiary. Okay, so primary, when you're talking about school, primary is your first school. So when you see primary, you should think of the number 1. When you see secondary, you should think of the number 2, because secondary is your first school. Your second school. What do you think about tertiary? Well, tertiary, you might have heard of tertiary education. Sometimes when you go to university, you call that tertiary education. So when you see tertiary in the context of alcohols, think about that as like the 3rd level of school, or perhaps college as well. Tertiary means 3. You should think of the number 3 when it comes to alcohols. Okay, so how do these numbers 1, 2 and 3 relate to the structure of alcohols? Well, if we have an alcohol, then there's always going to be a carbon atom bonded to the hydroxyl group directly. This is the carbon atom that you want to look at when it comes to classifying the alcohol as primary, secondary or tertiary. And what you're going to look at is you are going to look at the carbon bonded to the hydroxyl group, and you're going to look at the number of carbon atoms that it is bonded to. So if this carbon atom is bonded to 1 carbon atom only and 2 hydrogen atoms, then it's going to be classified as a primary alcohol. So just to show you the 3D structure, in a primary alcohol we have the carbon that's bonded to the hydroxyl group, and it is bonded only to 1 other carbon atom. Okay, so if this carbon bonded to the hydroxyl group is bonded to 1 other carbon, then it's going to be a primary alcohol. If, on the other hand, you've got a hydroxyl group, and actually the hydroxyl group has to be in the middle of a chain for this to be the case. The hydroxyl group can be bonded to this carbon atom here, and this carbon atom here is then bonded to 2 other carbon atoms. And if the carbon atom that's attached to the hydroxyl group is bonded to 2 other carbon atoms, then that's going to be classified as a secondary alcohol. So again, we've got our 3D structure here. We've got the hydroxyl group carbon, and then that one is bonded to 2 other carbons. So that's a secondary alcohol. Okay, so in a primary alcohol, the OH group is at the end of the chain. In a secondary alcohol, the OH group is within a chain, then in a tertiary alcohol, this last one here, in a tertiary alcohol, the carbon that's bonded to the hydroxyl group, this is the one that we have to look at, and we have to look at how many carbons it's bonded to. In a tertiary alcohol, the carbon bonded to the hydroxyl group is also bonded to 3 other carbon atoms, and it's this 3 other carbon atoms that makes this a tertiary alcohol. So again, let's look at the 3D structure. So we've got our carbon bonded to the hydroxyl group, and this carbon is bonded to 3 other carbon atoms here. And what this effectively means, in order for us to have a tertiary alcohol, the hydroxyl group has to be within the chain, and it also has to be at a branch position within the chain. So for a tertiary alcohol, the carbon that's bonded to the hydroxyl to be bonded to 3 other carbons, then the hydroxyl group has to be at a branch position within the chain. So it might be worth writing that down. Okay, so now we've got to draw and name a primary, secondary and tertiary isomer of the alcohol with molecular formula C5H11OH. A little hint for this would be to think about what we've just said here, to think about the position of the hydroxyl group in the chain and where that should be for primary, secondary and tertiary. So what I'd like you to do is pause the video just now and see whether you can do this question yourselves, and then I'll just pop the answer up once you've tried that. Okay, so here's what I've written here. I've gone for pentan-1-ol for my primary, although you could have had any isomer as long as the OH group, the hydroxyl group's at the end of the chain. I've gone for pentan-3-ol for secondary. You could have gone for pentan-2-ol or a branched version if you wanted, as long as the hydroxyl group is within the chain but not at a branched position, because that would make the alcohol tertiary. So our tertiary alcohol, the one that I've gone for, is 2-methyl-butan-2-ol. The main thing is that we need to have a branch at the same position as the hydroxyl group here. If you've done something else other than these 3, I'll mark it when you submit your work on Teams. So the final thing that we're going to look at in the alcohols section is diols and triols. These are reasonably self-explanatory. You should remember that the prefix di means, well, what do you think? Hopefully you're thinking 2, and tri, just like a tricycle, that means 3. So molecules which are alcohols can have more than one hydroxyl group. So far we've looked at just one, but molecules with 2 hydroxyl groups are called diols, and those with 3 are called triols or trihydric alcohols. So we've got 2 examples here. We've got glycol, which is ethane 1,2-diol, because the hydroxyl groups, the ol groups, are on 1 and 2. And then we've got another example here. This one, what do you think? Diol or triol? Really quite simple to see. 3 hydroxyl groups. This one's a triol, and its general common name is glycerol. Glycerol, is a really sticky chemical, which we have, I think, we have used sometimes in viscosity experiments. It's highly, highly viscous. So the first question here, question 10, says, what is the systematic name of glycerol? Well, think about the name of glycol. So glycol is ethane, because there are 2 carbons in the molecule, and it's 1,2-diol because there are 2 hydroxyl groups. Make sure you pause the video just now and think about what the systematic name of glycerol would be. Okay, so hopefully what you've come up with is there are 3 carbon atoms, so this name is going to be based on propane. Propane. Then we're going to have a dash just like we've got here, and this time we've got 3 hydroxyl groups on the carbon 1, carbon 2 and carbon 3. So this is 1, 2, 3 triol. Very important to learn the name and the structure of glycerol, because this is going to come up again when we look at the chemistry of cooking and when we look at fats and oils. So glycerol is given here, and its systematic name is propane 1,2,3 triol. Okay. Question 11, I've said, what are glycol and glycerol commonly found in? Just Google it. It's not mandatory knowledge, but it's a little bit interesting. And then question 12 says, glycol boils at 197 degrees C and glycerol boils at 290 degrees C. Glycerol is also more viscous. Explain these facts by analysis of the intermolecular bonding in both molecules. I should probably say intermolecular forces here, but never mind. Refer to both London dispersion forces and hydrogen bonding in your answer. So what I'd like you to do for this one is look at the structures of glycol and glycerol, and I'd like you to think about the relative strength of both London dispersion forces. So do they have similar London dispersion forces, or is one going to have a stronger London dispersion forces? And then I want you to also look at hydrogen bonding. So both of these molecules can form hydrogen bonds, but is there any difference between the ability of each molecule to form hydrogen bonds? And I'd like you to refer to both of these things in your answer to question 12. And I'd like you to explain which of the two has stronger intermolecular forces overall. Okay, so that is us finished. Once you've done question 12, that's going to be you finished with the alcohol section. I haven't written in your booklet, but if you need more practice, then you can use your blue revision book again. So if you think you need more practice of naming alcohols, then you're going to look at page 38 to 39. And just general reactions of alcohols. Well, we haven't really done reactions, but just if you want general questions on alcohols and naming, look at page 38 to 39. And then what I'd like everyone to do, just to double check your knowledge of primary, secondary and tertiary, is to try page 53. So it's a slightly different section of the book. And I'd like you just to do question 1 of that. And that's on a primary, secondary or tertiary. Just a wee aside, sometimes you see primary, secondary and tertiary written like this. I don't think it would come up in a chemistry exam, but it's just a little bit of background knowledge. Okay, thank you for watching the video. Please again let me know via Teams or via email if you have any questions whatsoever on this topic. Thank you. Bye.